Hello, my name is Jason. Hello, my name is Jason. 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 In the experiment, the radius will be changed to discover the corresponding oscillations. There's an unknown mass. My name is Jason. Says, however, without better technology to account for systematic and random errors, the experiment can hardly find better results. This experiment can be done by many and show decently accurate results. So my hypothesis was the mass of the stopper might be accurately found. There are many factors that are not included in the calculations that apply in the experiment. So for the materials, you'll need a meter stick, a known weight, a stopper, which was the unknown weight, a minimum of 2 meter plus string, Jason, 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 safety goggles, and a timing device. For the procedure, the live experiment done needed 2 people to accomplish, so that's why I had a lab partner. For safety purposes, both people should wear safety goggles to protect their eyes. First, put the string through the tube. The shorter end of the string through the tube will be the adjustable radius. Attach the unknown mass, the stopper, to the shorter end of the string. Next, attach the known mass more than 1 meter under the tube. Person A will spin the stopper by holding the tube. The person needs to try to keep the stopper spinning perpendicular to the hanging mass along with keeping a steady spin to minimize adjustments while spinning. As the stopper spins, person B will be recording the time it takes for the stopper to make 10 oscillations. When done recording the time for 10 oscillations, person A will have to carefully and precisely stop the string from spinning to get an accurate measure of the radius. A ruler should be ready near to measure the radius. Record the data. Adjust the radius at least 7 times just for more accurate data, and repeat starting from the step here. See? Repeat, repeat. So the table of quantities. The radius, variable r, units meters, and it's independent. Oscillation, variable capital T, seconds, is dependent. The stopper mass, as m for mass, and kilograms is controlled. In the table observation, the stopper number was labeled 6. The description was that there's 2 holes and it was at station 5. The mass in kilograms given was 0.02135 kilograms or 21.35 grams. So this is the data I've collected, and it looks pretty consistent. So in the graph, the relationship between the period of oscillation and the radius to solve an unknown mass in a uniform circular motion experiment. As you see, the accuracy, the coefficient of determination is 0.892, showing that the accuracy was pretty good. And you can see that they're mostly on the slope of the graph. So in the label diagram, I drew 2 free body diagrams and a rough picture of how the experiment went. So for the hanging mass, you have the force of gravity acting on the object, and you have the tension, force tension of the rope pulling the mass up. And on the stopper, you have the force of tension, and then you have the centripetal force of the stopper. So as you can see here, hanging mass this way, stopper this way. The 2 is the axle. In discussion, the force of tension in both free body diagrams are equal. So that means the force of gravity and acceleration acting on the known mass is equal to the centripetal acceleration acting on the unknown mass, the stopper. The equation for centripetal force is that the centripetal force is equal to 4 pi square radius divided by the period of oscillation squared. In our graph, we have gotten that the radius of a given oscillation equation is that the radius is 2.3 oscillations minus 0.623. So, using a random point to the slope of the graph to find the radius. I've chosen the random period of oscillation was 0.5 seconds. That gives me a radius of 0.517 meters, and I have to solve for what the mass would be. you get that the mass is 24 grams or 0.024 kilograms. So the percent error of that compared to the actual mass was 12.41%. The percent error of my findings is not high. So this is question. What is the radius with an oscillation with a frequency of 13 Hz? First, we have to say that the period of oscillation is 0.077 seconds. Yeah, now we solve. Using the equation, you get that the radius would be 0.0138 meters, or 1.38 centimeters. So in table errors, there was friction in the tube. It's a systematic error, because it will shift all my data. Inconsistent movement, not perpendicular when spinning the stopper, the recording of the oscillation time, and getting the radius after spinning the stopper are all random errors because they can be adjusted. They can make your results go up and down. There's also friction there and pressure there. To fix that, you would do an spin vacuum. All this requires better technology, and this is not really possible to have no friction, so you would say minimal friction of a tube. So in conclusion, the hypothesis states that the mass of the unknown object might be accurately found. The low percent error can state that the accuracy is higher than expected. If done correct and as precise as one can, the accuracy can be quite high. Our findings show that there is most likely a linear relationship between the radius and the oscillation. However, in the equation, t is squared, showing a nonlinear connection to the radius. Period oscillation. This might be due to the data being mostly within a small range of data of 0.2 seconds to 0.8 seconds, did not show the nonlinear connection. The seemingly consistent data could have been controlled due to a small range of data collected. The fact that there was such a high accuracy could also mean that the systematic errors of the force of friction could have shifted my data to make it seem more correct, as we did not equate that. Without better equipment, more accuracy cannot be done. In conclusion, the experiment in a small range of data might help one learn the basics behind uniform circular motion. We're excited. The textbook. My name is Jason. Smash that like button!